In question number 3, we're going to explore a recursive definition that looks a little bit different than the ones that we've seen up to this point. The interesting thing about question number 3 that you probably noticed as soon as you looked at the problem is that its recursive equation definitely doesn't have the same structure that we've been exploring and have probably come to expect due to the problems that we've seen before. We made it really clear in lesson 7b that a recursive equation usually is typified by that t of n plus 1 notation. And that's how we can usually tell that we're dealing with something new, recursive. This recursive definition doesn't have t of n plus 1. It has a t of n equals, much like the explicit equations we've been dealing with, but it also has a t of n minus 1, which is definitely new and not exactly the same as what we've been seeing, and we might have to chew on that for a little moment. So in letter A, if you can, try to put into words what makes this one different from what you've seen before. And the reason I'm asking you to think about this and put it into your own words is so that you can maybe start to think, what would t of n minus 1 mean? If we've talked pretty extensively about what t of n plus 1 is referring to, that if you're at a certain point in a sequence, n plus 1 is the next term, or the term after the one in question, then what might n minus 1 refer to? So take a few seconds, and if needed, pause the video so you have some time to think and write, and try to come up with an articulated answer for letter A about what makes this different. But see if you can also chew on that idea. You don't have to write anything, but think about that. What might n minus 1 mean? And why would this recursive equation be different? Again, if you don't have too much time to write, or if you like to take some time to sort your thoughts without the audio of this video getting in the way, then pause the video and definitely take some time to think about that answer. Instinctively, what I'm starting to think about in this n minus 1 kind of goes back to something I discussed in the previous lesson when talking about a table of values. How, and this is my scratch paper from the previous lesson, that if I'm at n, and n is any specific point in the sequence, n plus 1 would be the term after. So instinctively, n minus 1 is probably making us think of the term before. So this recursive definition is a little bit different because it's not telling us how to get to the next term forwards in the sequence. It's probably telling us how to go backwards and get the term before the one we're dealing with, which is kind of an interesting way of thinking about it. And that's not necessarily something that you're going to see in a lot of recursive definitions, but some recursive definitions are actually set up this way, that they tell you how to get to the term before the given term, not the term after. If that's puzzling to you, then I just want to make sure that I kind of give you a slight insight into the bigger picture of recursive definitions. Recursive definitions just tell you how to jump from term to term. Many of them, the ones that we usually focus on, tell you how to jump forward, but it's very possible to set up a recursive definition to jump backwards. And that flexibility is something to keep in mind, especially if you want to kind of think about this recursive idea. Maybe if this is something that interests you and this is a branch of mathematics you can see yourself actually trying to go deeper with, because many of the applications of recursive definitions actually build on that flexibility. For example, computer programming is actually a very common application of recursive definitions because computer programming essentially takes one small bit of data or one small command and then tells you how to iterate or perform the next and the next and the next and the next operation based on that beginning bit of code. And sometimes, if you program correctly, you can actually get a computer to program not only steps going forwards, but steps going backwards. So this idea of recursion or a recursive behavior can actually be a very interesting way of essentially creating a set of commands that make something happen. As long as you code it correctly, your commands can basically take a whole pattern in either way. Now, getting a little bit sidetracked there for a moment, I'll come back to the question at hand. In question letter B, it says, given only this information, what's the next term in the sequence that you can find? Now, if you're not really sure, and your instinct is like, well, okay, they gave me some information, but I'm not really sure what to do with it, consider making a table of values again. I'm personally a fan of tables for all sequence problems because I think it kind of helps me personally organize my terms. I think it helps me visualize where I am in a sequence, and I think it helps me kind of organize my info so I can see it in a bigger layout. Now, because they're giving us the 10th term as the starter value, I'm just going to kind of arbitrarily put n is 10 in this sort of middle of the table. That'll give me room to go both forwards or backwards, depending on which way I want to go. And since the 10th term is 8, notice my notation again. The 10 goes in the n spot because that's telling you where in the sequence you are, and the 8 is the value of the term itself. So here's what I'm proposing. I'm proposing that if n is 10, and n plus 1 would have given me the term after, and plus 1 would have given me the 11, and minus 1 might be giving me the 9th term. But to be sure, what I want to always reiterate is that you can use these recursive definitions not just as a guess as to what you think it might represent. You can take them really literally. You can take them as actual algebraic equations. If the equation is t of n equals t of n minus 1 minus 5, think of this like any sort of function that you've dealt with in the algebra world up to this point. We know, for example, that n is 10. We can make a substitution. We know a fact about n as 10. So we can substitute the number 10 for the letter n, and we can actually do a bit of algebra with this. Same thing in the other right-hand side of the equation. We know that n is 10. We can make that substitution because that is a given fact. That is something that we can actually substitute because we know that n can be 10. They gave us that in the definition. Now, if I look at this algebra here, I'm going to kind of let my algebra instincts take over. Even though I might not necessarily know what I'm doing or why I'm doing it yet, just kind of roll with the instinct that builds here. Because I'll bet your instinct is to say things like, oh, well, 10 minus 1, I can clean that up. So let's just kind of let our instincts ride for a moment. 10 minus 1 is 9. So now if I rewrite what I've got, I had t of 10 equals t of 9 minus 5. And I'm looking this again, asking myself, wait, hold on. I know something here. T of 10. We know something about t of 10. T of 10 equals 8. They told us that in the original recursive definition. That's a fact. The 10th term is 8. I'm going to substitute the expression t of 10 with the number 8 because that is a legitimate substitution I can make. And now that I look at it, I'm kind of saying to myself, hey, wait a minute, t of 9. T of 9. That would refer to the 9th term. Maybe I was right about my initial supposition. Maybe this definition is going to give me the 9th term in the sequence. Let's hope anyway. If I look at this expression, though, t of 9, it looks like it's kind of stuck amidst this algebra. So again, I'm letting my algebra brain take over here. What if I move this 5 by adding it to the other side to get t of 9 by itself? Then I have t of 9 on the right-hand side equals 8 plus 5, 13. Let's parse this for a moment. T of 9, the 9th term in the sequence, must be 13. I just kind of solved for it algebraically. But now that I write that in my table, I'm going to reflect for a moment. That does seem to kind of make sense with what the recursive definition was telling me. If the recursive definition was telling me to find the n minus 1th term, which is the term before the given one, it's kind of like saying, yeah, the term before it, minus 5, was going to give me the 10th term. And sure enough, 13 minus 5 was going to give me 8. Now, if that reasoning is a little bit convoluted, but you followed the algebra, that's fine. It doesn't matter how it makes sense. But notice something. We now have a really distinctive pattern. We now know 2 terms in this table, and this will give us enough information to generate as many terms as we want to, because we can see the pattern now. 13 minus 5 is definitely 8. So even without doing a bunch of algebra, I can kind of take the easy route here. I know that if the pattern continued, 8 minus 5 must give me the term after, and 3 minus 5 must give me the term after, and so on and so forth. I know the pattern now. I can see it clearly, and I can definitely keep going and fill in more terms. If I wanted to, I could also go backwards. I could say, oh, well, if I know the 9th term, I can predict what came before it. I can predict the 8th term, because something minus 5 would have given me 13, so I can work backwards and predict subsequent terms before the 9th. But notice how this one kind of gave us a really interesting way of generating that term. That instead of just interpreting the recursive definition, we actually could solve it as if it was an equation. And that's important to note about these recursive things. If it confuses you to use these recursive definitions as like a clue, if you look at it and you're like, I don't really know what this is saying, t of n minus 1 minus 5, I don't really know what that means, then don't panic. You don't have to interpret it. Just treat it like an algebra equation. Make a substitution with the math that they give you. Usually the given term is a substitution you can make. And use your algebra skills to solve for another term. Once you know what you're solving for, that's usually enough of a clue to unlock the pattern. And once you unlock the pattern, your common sense can kick in. You don't have to do algebra for every single term in the table. Usually just doing algebra to unlock one term is enough, because then your instinct can kick in and you can use the pattern, a basic pattern like subtracting 5, to get you through. So now that you've seen how this pattern works, let's see if we can go back and do the rest of question number 3. It said in question letter B, given only this information, which refers to the initial question, what is the next term in the sequence that you can find? Well, they gave us the 10th term, and when we plugged it in, the only term that we were able to solve for was the 9th term. And again, some of us predicted that because we knew that n minus 1 probably referred to the term before the given one, hence the 9th. In letter C, it says to determine at least 5 terms in the sequence. We did that in our table here. You obviously can do any 5 terms in the sequence. If you wanted to carry the sequence even further backwards, you could do the 1st, 2nd, 3rd, 4th, and 5th terms. If you're comfortable with the ones we did here, you can do the 8th, 9th, 10th, 11th, and 12th terms. You can write any 5 terms in the sequence that you want. It doesn't matter which ones. Now in letter D, we have to do a little bit of critical thinking, because it says to determine the initial value of the sequence. As you probably recall, the initial value is the 0 term in the sequence, and that is quite far away from what we have in our current table. I stopped at the 8th, admittedly, because I got lazy, but that implies that if I went backwards and backwards and backwards, really quite far, I should be able to get to the 0 term by simply adding 5, adding 5, adding 5, adding 5 to keep going back and back and back. The only downside to that, I mean, it sounds easy, is that it sounds kind of tedious. So let's talk about a couple of ways that we can do this. Obviously, one way is to just make a gigantic table, leave yourself some space, and see if you can figure out how to make it go backwards. Another option is to ask yourself, do I have any algebra here? Could I think of anything that could work? Because in theory, we can piggyback off of letter E for a moment. We do have enough information to kind of start to think about an equation. And if the only unknown thing is the initial value, we could start to think about the algebra involved and maybe see if we can come up with something. Remember that the explicit equation structure is to take the initial value, I'll call it capital I, plus the adder, which I'll call capital A, times n. Now, I'm just using these capital I and capital A as placeholder values. Those are not really official variables in any sense, but I want to think about this for a second. I don't know the initial value. I'll call that the capital I, but I do know that the adder of this sequence is -5. Because each term in the sequence is 5 less than the one before it. That's what we've been calling the adder this whole time. So I know that that A is really -5. The negative kind of trumps the positive plus sign, so that's why I'm using a minus sign there. Now, when I look at this equation, it still looks a bit of a mess. It still looks like that I have all sorts of unknown things. I want to solve for I, but I also have a variable n and a variable t of n. That doesn't look too good, except, now I'm thinking for a moment, n and t of n could be anything. N and t of n could be any combination of real numbers that I know works in this sequence. For example, the 10th term is 8. I know that already. So if I want to just piggyback on the idea of substitution, and it's almost kind of like using a system of equations where you use some clues and try to plug in what you know. It almost reminds me of like when we plug in and solve for a values of parabolas. We plug in given points to solve for the parameter we don't know. Let's see if we can take advantage of this. I still don't know the initial value, but I do know that if I want the 10th term, which is when n is 10, t of n, the 10th term, would be 8. I can make that substitution. And now that I look at this, I definitely have an equation that algebraically is very doable. The initial value, which is I, minus 5 times 10 is 50. It looks like I can solve for I. And if I move the 50 to the other side, it looks like I can solve for I and get 58. So my supposition then is that if this is correct, 58 must have been the initial value of the sequence. Now, some of you might be sitting there watching me do all of this saying, oh, Herbert, you're being silly. In all of that time that you took to do this algebra, I just kept going backwards. And that might be true. If you're pretty good at just doing quick mental math and you just kind of took the 8th term and then went backwards, did the 7th, the 6th, the 5th, the 4th, the 3rd, etc., and just went all the way back to the 0 in no time flat, you probably already knew that the initial value was 58. But this proves to you that you can actually figure out the initial value in a couple of different ways. And what I want to make sure I show you is how if you have a graphing calculator, you can actually capitalize on that information. If you have a graphing calculator at home or an app that suffices, you can actually use the table feature to help you quickly generate some terms and verify these things. If in my y equals part of the calculator, I type what I think would be my new explicit equation. So I think that my initial value is 58. I know that my adder was -5. So I'm going to type 58 for the initial minus 5x, because my calculator is in terms of x, not n, but close enough. And then I'm going to go to the table. Now notice something. Remember how they said that the 10th term of this sequence needed to be 8? Well, 10th term in this table is 8. We did our scratch work and said that the 9th term needed to be 13. There it is. 8th term needed to be 18. There it is. The 11th term was 3. The 12th term was -2. There they all are. So the beauty of a table is that you could actually generate all the terms really quickly. Sure enough, there's my initial value of 58. And you can see the table on the screen as well. If you have a graphing calculator, this is actually a great tool that helps you check your explicit equations very quickly, because if you type in an explicit equation, the table automatically generates itself. In any case, it seems as though we have answered successfully question letter D and question letter E. We know that the explicit equation is definitely T of n equals 58 minus 5n. Now, let's think about question letter F. Question letter F says find the 85th term in the sequence. And I'm thinking about my scratch work, my table, going, oh dear, that's going to take a while. Because I stopped at 12 feeling like I had done enough. And extending it to the 85th term, that doesn't sound too helpful. So let's think critically. If I need to find the 85th term, that means n has to be 85. What would make the most sense? I'm thinking that if I know n is 85, I could plug in that 85 to my explicit equation, and that should be able to tell me the 85th term. Let's verify, see if that's true. T of, make a substitution, n is 85, equals 58 minus 5 times, again, n is 85, a substitution. T of 85 just means the 85th term. I don't know that, so I'm just going to leave that as an expression. But 58 minus 5 times 85, a quick multiplication, should give me 425. And 58 minus 425 should be negative 367. Now, I don't really have any context, but I mean, I guess that sounds right. If I'm looking back at my scratch work table, the numbers were getting kind of negative already by the 12th. So if I was at the 85th term, I'm probably going to be quite negative at that point. That makes sense. But here again is where your calculator comes in handy. Remember how we had already typed in our explicit equation? If you go to the table, you might now think, oh gosh, do I really have to scroll all the way down to the 85th term? These calculators have a wonderful feature in the menu called Table Settings, which is accessed by pressing Second and then Table Set. If you type where you want the table to jump, in this case I want it to jump to the 85th term in the spot that says Table Start, and then go back to your table, it kind of teleports you to that term. And sure enough, the 85th term is negative 367. So, the moral of the story is that either way we go, the easiest way to get to the 85th term was definitely to use the explicit equation. And that's something that going forward you might want to think about. I had this recursive definition, but I didn't really use it to find the 85th term. I want you to chew on that idea. Why? Why was the explicit equation more helpful here? As you're chewing on that idea, I'm going to ask you to try question number 4, and because it kind of continues on to the next page, question number 5. Questions 4 and 5 refer to the same sequence of numbers, but again, it's going to ask you to sort of think about that idea. Which equation, explicit or recursive, would be more useful to answer some of these questions? Chew on that idea, and in the next video, we'll try to formalize some of those thoughts so that you can think about them in a more constructive way.